Geochronology is a branch of science, specifically geology, which studies the dates or the ages of rocks. And the reason we need to know the dates or ages of rocks is because they don't come date stamped. Geologists have used many different ways to date rocks. Geology as a science has been around for a couple of hundred years now, and originally the only way we had of putting dates on rocks was something that's very grandly called William Smith's law of superposition. And all this means is that if you have a sequence of rocks, one on top of each other, the rock at the bottom must be older than the rock at the top. It's very straightforward. It's purely applying the laws of gravity to material moving across the surface of the planet. It sounds very simplistic, and it is, but it's very important, because only if we know the age sequence of a series of rocks can we work out the age sequence of a series of events, whether they be different depositional environments or rocks with different sorts of fossils in them. And this is called relative dating of rocks, i.e. if the rock underneath is older than the rock above, then anything that we find in the rock underneath must be older than material we find in the rock above. And this is how stratigraphy was established. Again, in geology, we tend to talk about stratigraphic columns because we have rocks ordered in a time sequence. So a stratigraphic column would represent a sequence of rocks with the oldest at the bottom and the youngest at the top. Stratigraphy very early on was then used to look at fossils. People started to notice that you only found certain fossils in certain rocks, and that wherever you found those rocks, you would find them in the same relative position in that stratigraphic column. And so we found we could use fossils to date rocks. But again, this was relative dating. It was saying that I found this sort of fossil in this rock, and we know that that sort of fossil is found lower down in the stratigraphic column, so therefore it must be older than the fossils in the rock above it, which were a slightly younger species of fossils. And this is the only way we could date rocks at all until we developed geochronology. The big difference between geochronology and using stratigraphy or using fossils is that geochronology gives you absolute dates. It gives you a date with a unit attached. It's not younger than or older than, it's 3,256 million years plus or minus 6 million years. And that's an important and unbelievably overwhelming contribution to the science of geology. Radiogenic isotopes were only introduced to geology in about the 1950s. The use of them for dating strongly relied on the use of mass spectrometers. So it wasn't until mass spectrometry was developed by physicists that geologists could then take that over and start to use radiogenic isotopes to date rocks. However, really, we didn't start to make huge advances in the very, very old rocks we're talking 2,000 million years old plus, rocks of 2, 3, 4,000 million years old, until the shrimp was developed. And the shrimp stands for Sensitive High Resolution Ion Microprobe. The big difference between the shrimp and the thermal ionizing mass spectrometer is sample size, and you can put the actual sample that you're wanting to analyze in the machine, and you analyze something that may be as small as 20 microns across, being remobilized. So therefore the date that you can calculate from a shrimp analysis, you know is related to the date that that zircon or whichever other mineral crystal you're looking at was formed. And that was really a major leap forward. That allowed us to look at very old rocks and really be confident that the dates that we were calculating were the date of the minerals in those rocks and not some other geological process that's happened to them since. The minerals we use to date very old rocks are important because we have to select certain minerals that preferentially incorporate uranium into the crystal structure, but if possible, leave out the daughter product. This means that when we analyze these minerals, we know that all of the lead that we've analyzed has been produced by radioactive decay. And that means that we have an enormously precise ratio, and this helps give us a very precise and accurate date. And the best mineral that we have found to do this with is a mineral called zircon. Some of you may be familiar with zircons from looking in jewelers' shop windows, because zircons are widely used in the jewellery industry to look like diamonds, because they have many of the same qualities, the same appearance of diamonds. We find them much more interesting than diamonds. You can't use diamonds for geochronology, you can use zircons. Now, this is an example of a very large zircon. It's a centimetre-sized crystal, very, very unusual. You would normally not see anything of this size in a rock that you were dating. Normally zircons are tiny, usually less than 100 microns across, and in fact this sort of sample size is much more like the sample that we're normally dealing with. What we have to do is we have to separate those zircons out, again between 50 and 100 microns, and then put them into the mass spectrometer where we can then analyse them. Zircons crystallize from a liquid, from an igneous liquid, so they're mainly produced related to volcanic activity. And what happens in nature is that as igneous rocks and volcanic rocks are brought up to the surface, as is very common in Western Australia, is that minerals that are resistant to weathering are eroded out of those rocks and are then transported by rivers to produce sediment like sand on the beach or the dirt that you see around you. In fact, if you go onto many beaches in Western Australia and pick up a handful of sand, there will be many zircons in that sand. That sand sits there as a sediment and slowly is buried by more sand coming on top of it, and groundwater moves through the spaces between the grains and precipitates more minerals. That process is diagenesis, which is the process that turns sediment, loose grains of something, into a solid rock. Now, if there are zircons sitting in that sediment on, say, the beach, then if there is uranium in the water that's moving through the rock, what happens is that the zircon will form an overgrowth or a fringe. The overgrowths that form around zircon, precipitated by the groundwater, are not the same mineral as zircon. There are many different minerals that are precipitated by groundwater, and one of these is xenotime. Xenotime is an yttrium phosphate, so it's a rare earth element-bearing mineral, but it also takes a lot of uranium into its crystal lattice. And so effectively, what we can now do with that piece of rock formed on the beach somewhere in Western Australia is we could take a thin section of that, we'd see the zircon, but we'd also see this maybe 10 or 15 micron wide overgrowth of xenotime. And using the shrimp, and you could only do this using the shrimp, you can date the zircon in the centre and you can date the xenotime overgrowth. And it's that xenotime overgrowth that tells you how old that sedimentary rock is. Because of course the date that the zircon tells you will be the date of the original igneous rock from which that zircon grain came. A really good example of the application of shrimp dating is the Stirling Ranges in southwestern Australia. The rocks that make up the Stirling Ranges are sands and siltstones, very much like you'd find on the beach at Geograph Bay today. And those rocks are 1100 million years old, according to a date that was published in the 1960s. But we've also found fossils in the Stirling Ranges. They're not body fossils, but they are trace fossils, the traces that creatures make as they go about their daily lives. So for instance, you leaving footprints in the sand, that would be a trace of the fact that you were walking across the sand. The fossils in the Stirling Ranges are very important because these are very old fossils. As I've said, we had an age of 1100 million years on those rocks. So what we thought we'd do is we thought we'd check that age by using the shrimp. So we analysed the rock, we found that there were zircons in there, we found that there were xenotime overgrowths on those zircons, formed by exactly the same process that will be forming xenotime overgrowths on the zircons on the beach today, i.e. the groundwater moving through the rock. The dates from those xenotime overgrowths are close to 2,000 million years. So we now know that the Stirling Ranges rock was forming a rock, a sedimentary rock, on a beach 2,000 million years ago, not 1,100 million years ago, as the rubidium-strontium date gave us. What the rubidium-strontium date was actually giving us was another geological process, which was a huge continent-continent collision process that was happening in that area at the time, which reset the rubidium-strontium clock. This is of immense importance to have evidence of life on this planet close to 2,000 million years old, which is almost half the age of this planet, is hugely important. And the fact that it's here in Western Australia is extremely convenient for us because it means we can go and look at the environment that that life was living in.